So today we're working on practicing and reinforcing what we learned in the first day of geometric sequences. We're going to go through some of these like refresher problems and talk about them. We have determined the missing terms from the sequences using recursive functions. So remember recursive, the key thing of that is that we're going one by one. So we're going one term at a time. We're not able to jump forward in the sequence like with an explicit formula. So here we have f1 is 0.5. I'm going to change that to 1/2 because decimals don't play well with sequences. And then f of n is 4f of n minus 1. Remember that this means the nth term, so whatever term we're trying to find, but it says it's 4 times the previous term. That's the nature of recursive and why we can only go one at a time, is because each term is something times the one right before it. So if we don't know the one right before it, that doesn't help us. But when we're writing out a sequence term by term like we are here, then it's great. So we can put 1/2. 1/2 times 4 is 2. 2 times 4 is 8. 8 times 4 is 32. And 32 times 4 is 128. Here, we don't know what f1 is in the definition, so in our recursive definition here, we know how it changes, so that's the second part, but we don't know where it starts. So we need to look at our actual sequence listed out here and identify that the first term is -3, so that will be f1 equals -3. We start at -3. And we change, in this case, this is a plus, so this one is going to be an arithmetic sequence. It says that we're adding 3/2 to the previous term. So whatever term we want to find is the one before it plus 3/2. So -3 plus 3/2, so we might want to think of that as -6/2 plus 3/2 is -3/2. -3/2 plus 3/2 is 0. 0 plus 3/2 is 3. 3/2 plus 3/2 is 6/2, which simplifies to 3. And 6/2 plus 3/2 is 9/2. So that fills that one in. The next one, we have a subtraction. So this is another arithmetic sequence. We don't know term number 1 in either location. So we're going to have to think about how we could go here. So going forward, we know that we're subtracting 6 at each step. So here we go, -12, -18, and then -24. But in order to go backwards, we need to reverse the operation. So to go backwards, we need to add 6. So that means that we have 0 as our initial term, and we put 0 here as term number 1. The next one, we don't have term number 1 in the definition, but we have it in the sequence, so we can copy that up here as 5. This one is interesting because it's written a little awkwardly. It says any term is the one before it divided by 3. The normal way that we write that is 1/3 times f of n minus 1, or a n minus 1. Remember that this can be written as a subscript or as parentheses, either way. But here we're multiplying by 1/3 or dividing by 3 at each step. So this is a great example of why we don't want to use decimals. So we have 5, then 5/3, and then to keep dividing by 3, we're basically just multiplying the denominator by 3. So we go 5 over 9, because 3 times 3 is 9. 9 times 3 is 27. And then finally, 3 times 27 is 81. So we get 5/81 as our fifth term. Number 5, we don't know term number 1, so we're going to do like we did earlier, but also we don't know the common difference. So we're missing both pieces of information in our definition. We don't have the start, and we don't have what it's changing by. So let's look at our sequence. We can see right here, we know it's a plus, so we know it's an arithmetic sequence. This is adding 4. So then if we add 4 again, we would get 33. Add 4 again, we get 37. So that all looks good. We're adding 4 at each step. And then remember to go backwards and find a previous term. We're going to subtract 4, and that takes us to 21, which would be our initial term. Next one, we're starting at -100. We're multiplying by something, but we're missing every second term. So this is maybe the hardest one of all here, because we're going times something and times something. So let's call this x and x. So we have -100 times x squared, because we've multiplied by x twice, equals negative 225. So we can divide by negative 100 and get x squared equals positive 2.25. 2.25 is like 225, which is 15 squared, but it's shifted over twice. So that would be like 15 over 10 that we're multiplying by, because 15 squared is 225 and 10 squared is 100. So we're multiplying by 15 tenths, or 3 halves at each step. Now, if we're not confident in the math that we just did, we can check our answer. So we have negative 100 times 1.5 would be negative 150. Half of negative 150 is negative 75, and that would indeed take us to negative 225 as our next step. So then we would do 3 halves times negative 225. I would leave that as a fraction and do negative 675 over 2. And that way, when we go to the next step, we don't need to do negative 506.25. We could just multiply the numerator and denominator by 3 and 2 and avoid using decimals here. Okay, so our first term was negative 100, and we figured out from taking 2 steps and square rooting it, basically, so we square rooted this, that our multiplier here was 3 halves, or 1.5. Okay, so we just did some comparison. We saw some geometric sequences and some arithmetic sequences. This alike and different is about comparing those yet again. So here we can see that each step we're adding 2. And then here we can see that at each step we're multiplying by 2. So times 2 times 2. And the big takeaway here is that as we go through an arithmetic sequence, it's growing in a linear fashion. So it's a nice straight line with a constant rate of change. Whereas this one is going to form a curve that grows faster and faster the further we go forward, because if you think about how much it's rising, we had plus 3, plus 6, plus 12, plus 24. So it's growing by more every single step we go forward, and it's going to curve up and get steeper and steeper. All right, next 2 terms in the table. I don't see a table. Oh, above. I see. There's more to do here. So we're going to complete the table. Sorry, we're going to do 6 and 7. 6, 7. Everybody loves 6, 7. That's good. So we go 13, 15. Here we double this and go to 96. And then 96 doubled would be 8 less than 200, so 192. Well, we're not going to be able to graph all of that on this coordinate grid, but we can graph some of it. So our first one, term number 1, is 3. So we'll do this one in blue. 3 is about here because that first line is 5. And then we're adding 2 at every step. So we had 2, 5, 3, 7, 4, 9, 5, 11, 6, 13, 7, 15 would be right here. Was that as far as we go? We went to 7, right? Yeah, okay. So the other one we're going to do as a set of red dots to differentiate it. And remember that here these are discrete because this is a sequence, so we're not like connecting the dots with a line or anything. It's just individual single dots, and there's none on the y-axis because we start at term 1, so we don't have like a y-intercept. On our geometric sequence, we had 1, 3 as our first point again, so these overlap, they're coincident. And then from there, we're doubling each time. So we had 3, next we went to 6, then we went to 12, which would be up here, then 24, which is almost 25, then 48, which takes us to the very top of our graph right here, and then those last 2 terms we can't even fit on the graph. They'd be way, way off the graph. So how could we describe each one? We could say that the blue one was linear. It forms a straight line. The other one is a curve, and specifically we call this type of curve where we multiply by the same thing every time exponential, which means it's growing faster and faster. So things that we notice, they are discrete, they are increasing. So even though they're increasing in different ways, both of them are still going up as we go forward. What else? That's good enough. All right. List whether each is arithmetic, geometric, or neither. Include growth rate if it is a sequence. Growth rate is an interesting thing here, so we'll see what we have. So here I can see 3 to 8 would be times something terrible, but it's plus 5. This is also plus 5, plus 5, plus 5. So this one is arithmetic. And we have a common difference, which is equal to 5. The next one, we have minus 12, minus 6, minus 3. So it's not arithmetic, but if we look at it as geometric, this is 1/2, this is 1/2, and this is 1/2. So that would give us 1/2 at each step, and we would have a geometric sequence, and our common ratio, r, equals 1/2. The next one is switching signs back and forth. Arithmetic sequences can't do that, but geometric can. So here, if we did geometric, this would be times -2, times -2, times, and so on. So these are all times -2. So this one is geometric, and it has a common ratio of -2. And then this last one is plus 3, plus 5, plus 7. So that's definitely a sequence because it's a predictable pattern, but it's neither arithmetic nor geometric because it's adding a different number every time, and it's not multiplying by the same number every time either. If we looked at multiplication, this is times 2.5, times 2, times 1.7, right? So it's not the same either way. So this one is neither arithmetic nor geometric. Okay, first 6 terms of geometric sequence. So this one we're still doing recursively. We're not doing any explicit formulas here because we're going step by step. We have an equals 2 times 3 to the n minus 1. So this is a geometric sequence. It is a geometric sequence. It's also a explicit formula, but we're going to use the formula recursively to find each term one at a time. So let's see, we're going to do first 6. So 1, 2, 3, 4, 5, 6. So as a reminder, if we did want to use this explicit formula and not go one by one, then we could jump directly to term number 6. By doing 2 times 3 to the 5th power, because we plug in 6 up here where it says n minus 1, and we end up with 3 to the 5th. I'm not sure what is 3 to the 5th. That's 3, 9, 27, 81, 243? 243. So we could do 2 times 243 and jump straight down to 486 as term number 6 if we needed to. That's the power of this formula, whereas doing it recursively the way we did above in the earlier examples, we can only get to term number 6 if we go one by one through each of the others. So our common ratio here is 3. That's the thing we're multiplying by each time. Our initial value is 2, so not initial value, our first term of the sequence is 2. 2 times 3 is 6. 6 times 3 is 18. 18 times 3 is 54, and 54 times 3 is 162. 162 times 3 is 486, so that all looks good. On the second one, we've reversed the two things. So now 3 is going to be our first term. We still do 1, 2, 3, 4, 5, 6 for the term numbers. But now our common ratio is 2 instead of 3, so we're doubling at each step. So again, if we wanted to jump ahead to step 6, that would be 3 times 2 raised to the 5th or 6 minus 1 power. 2 to the 5th is 2, 4, 8, 16, 32. So 3 times 32 would give us 96. So that's how we can jump further ahead in the sequence. Remember, if the exponents get bigger to where we can't do, these are not, these are reasonable numbers, but if the exponent gets bigger or you have a big common ratio, then we're going to need to use a calculator to do those, but these are simple enough that we don't need one for these. So we have 3, we double that, we get 6, we double that, we get 12, 24, 48, and then yes, 96 would be the next term in the sequence. Okay, then to close out today's notes, we have some word problems. So this first word problem is about a bungee jumper that's jumping from a bridge. And we have the table showing his height above the ground at each bounce. So basically, you bounce the most on the first one when you have the most kinetic energy that's rebounding you back up. And then each time you bounce a bit lower until you kind of just hang there at the end. So after bounce number 1, this bungee jumper goes up 200 feet, then up 80 feet, then up 32 feet. So if this is a geometric sequence, then we should be dividing by the same amount or multiplying by the same fraction every step we go forward. And we want to know the height at the 5th bounce. So we're going to extend this table a little bit. We're going to figure out our common ratio. So to find the common ratio, we can take any number and divide it by the one right before it. So that's why it's a ratio. It's a ratio of the next term to the previous term. So our common ratio, R, is going to be 80 over 200. First thing we can do is cancel out one of the zeros and turn this into 8 over 20. Then we want to simplify this down. So 8 over 20 are both divisible by 4. So if we simplify it by 4, we get 2/5. So then we should check if the next step is also 2/5. So is 80 times 2/5 equal to 32? 80 divided by 5 is 16. 16 times 2 is 32. So we do have a geometric sequence. I know they told us it is, but it doesn't hurt to check. So the next step down, we're going to multiply by 2/5. So remember that 32 is the same as 32 over 1. So if we're multiplying by 2/5, the numerator will be 32 times 2. That's 64. And the denominator will just be 1 times 5, which is 5. If we wanted to simplify that, it would be like 8.8, but no, not 8.8, 12.8, 12.8. So we don't need to turn that into a decimal unless we're asked to. And the fraction is easier because when we want to go to the next step, 64 over 5, if we multiply by 2/5 again, that just makes the numerator 128, which is 2 times 64, and my denominator would be 25. That would be 5 would be 125. So that would be 5 and 3/25 if we wanted to convert that into like a mixed number, or if we did a decimal, 3/25 would be 1.2, right? 5.12. So yeah, we can do whatever format here, but I would just stick with fractions because it's the simplest. So height after the 5th bounce would be 5.12 feet, or 128/25 feet. All right, we have, let's see, we have 3 more, so we'll go through those. So Leo's bank balances at the end of months 1, 2, and 3 are 1,500, 1,530, and 1,560.60. They form a geometric sequence. And we can see that because here we added 30, and here we added 30.6. We're not adding the same amount each time. When we have a geometric sequence or an exponential growth on a bank account like this, we call that compound interest. So what will his balance be after 6 months? So we have 1, 2, 3, 4, 5, 6. Although in this one, I'm actually going to go ahead and get the calculator out, and we're going to do this one using Desmos and using an explicit formula because we haven't done much practice on explicit formulas so far today. So we know that our AN is going to equal the first term, 1,500, times something to the n minus 1 power. The only thing we need to do is find that times something. So to find the something, just like in the last problem, we can divide any term by the one before it. So 1,530 over 1,500. Again, we can cancel out a 0. Now, both of these are divisible by 3, so that would be 51 over 50. No way to simplify that, so our common ratio is 51/50. So now we can get Desmos involved and find out what after 6 months is and maybe fill in the rest of these as well. So let's get Desmos. Okay, Desmos. So we're going to use this formula. Instead of an, we can put y equals, or we can just put the right-hand side because Desmos knows that we mean y equals. So I'm going to put 1500 parentheses 51 over 50. It's important we put the parentheses there to make sure that the entire ratio here is raised to the exponent and not just like the 51 or the 50 individually. So the parentheses are going to force the division to happen before the exponent, which normally it wouldn't, as we know, because exponents happen first. Then we use a to the b in order to raise it to the power. And then n minus 1, if we wanted to graph this as an exponential curve, we could put x minus 1. And we have to put parentheses in the exponent as well so that it doesn't drop back out. And we end up, since our y-intercept, or our initial value is 1500, our term number 1, we're going to have to zoom way out in order to see this curve. So here's our curve. It looks like this, but we don't need all of that. We just need specific values. In this case, we want Leo's balance after 6 months, so we can replace x with 6, and we can find the value as 1656.12. Since we're talking about money, we're going to round to 2 decimal places because that's how dollars and cents work. We can also see that as given in the problem with 1560.60. So we have the answer after 6 months. Leo would have 1656.12. So just out of curiosity, I'm going to add a B part here. What would it be after 5 years if we kept going at that interest rate every month? Then we know that our x value for 5 years, if we're compounding monthly, because it's going month 1, 2, 3, that would be equals 60 months. So let's go back to Desmos and change our 6 to 60 and see what happens. So this would be after 5 years. Now, instead of, because 1656 didn't look like it went up all that much, but we also had gone through a very short change in time. But if we go 5 years into the future, now he has $4,825, which is more than triple what he started with at this interest rate. So that's pretty good. And this is only a 2% interest rate, so it shows you kind of the power, if you don't remember compound interest, that when you grow things exponentially, they grow really, really fast compared to like a linear growth rate. Okay, then the last two we have, evaluate 2 situations. Suppose all terms of a geometric sequence are positive and the common ratio is between 0 and 1. Is the sequence increasing or decreasing? So one way to do this would be to make an example for ourselves. So all terms are positive, including term number 1. So let's say that we'll make a table here. Let's say term number 1 is 50. Then let's say that our common ratio is equal to just a half, would be something between 0 and 1. So then term number 2 would be half of that. Term number 3 would be half of that, and so on. And things would be getting smaller and smaller. So as long as the common ratio is less than 1, then we're getting less than we started with each time. And that kind of makes sense because you're multiplying by something less than 1, so you end up with less than you started with. So this would be increasing. And when we get to exponential functions this week, you're going to see that we call an increasing exponential function a growth function. So increasing linear we called positive. Increasing exponential we call growth. No, this is decreasing. Why did I just say that? So this is decreasing, which is called decay. So we got both vocabulary in here. So if it was linear and decreasing, then it would be called negative, like a negative slope. But exponential decreasing we call exponential decay, meaning this value is kind of dropping closer and closer to 0 the further we go forward. It's never going to reach 0 because no matter how many times we divide this in half, there will still be something there, but it will get like infinitely small as we go forward. Okay, if the common ratio is less than 0, what do you know about the signs? So we saw one of these earlier. Let's just make ourselves another example. So here we can do r equals -2. term 1, 2, 3, 4. Let's start at 10. So if we start at 10, the next term would be negative 20, but then the negative times negative is going to turn this into a positive 40. Negative 2 times 40 is going to be negative 80. So we can see that the sign switches every time. And this actually doesn't make an exponential function, because exponential functions are only, they have to have the same sign. So they're not going to be able to alternate. So let's compare just graphically. If we did y equals, what did we do? 10 times 2 to the x minus 1. Then we get kind of a regular old exponential curve. But what if we try to do y equals 10 times negative 2 raised to the x minus 1? Then I don't think, Desmos can't even graph what that would look like, because basically it's infinitely oscillating between positive and negative, switching back and forth, and it just doesn't work. So the TI calculators try to graph it, and it just kind of looks like a huge mess that like makes the calculator look like it's having a seizure. But Desmos is not playing games. It won't even try to graph it for us to let us see the nonsense. Okay, our last problem for today is to write an explicit formula for this sequence. We have the value of a house starts at 150,000 and increases by 1.5% per year. So this one's a little bit tricky, and it leads into talking about things like compound interest and exponential functions. We know that if we were writing this as a sequence, an equals 150,000 times something to the n minus 1. It always looks like this for explicit formula. But if we put 1.5%, remember percent means over 100, so we would need to move the decimal place 2 spaces this way. So this number is 0.015. From the questions we just answered, I know that if I put 0.015 here, then we're going to have a decay function. It's going to be dropping down towards 0, because every time I multiply by 0.015, my number gets smaller. But this problem specifically says that this is increasing. So we need to think about what that means. It's very similar to how compound interest works, in that if we're increasing by 1.5%, that means we still have 100% of what we started with plus 1.5%. So that would mean 1 plus 0.015. And if you remember the formula for compound interest, it looks like this. It has 1 plus the rate that you earn on your account. So this is how we go from a number that looks very, very small to actually causing an increase in value, because we have to account for the 100% that we already had. We're not losing that. We still have it. We're getting an extra 1.5%. So that would be 1.015 here. And that's all the notes for today. There's practice stuff in OneNote, practice in Delta Math, and other stuff to do.